Okay. Hello everyone and welcome to class. So how was your reading week? You could take a rest during the reading week, or you were like too busy with the midterms and exams? So how was the midterm for this course? How did you find the midterm for this course? Fair? How many of you think it was fair? So, okay, sounds good. Is there any specific question in the midterm that you want to clarify? Okay. So today I'm going to start on K-nearest neighbors as another model for classification. So far we have spent a few sessions on decision trees. For KNN, it doesn't need that much time. We only spend one session. We will also have prepare some questions on Kahoot again, so we can just review some sample questions in KNN together at the end of this class. So the idea of the K-nearest neighbor is that to find the actually the distance with all the training examples, and then finding the ones with the minimum distance, or the ones that are more similar to the like the new example that we want to predict the class label for. And so this is like based on the idea that you may have heard that say you can know someone with the people that he or she is hanging out with. So you are there's also a common a popular quote that you will become like five people who you spend more time with. You become more similar to them. So this is kind of the same. So you can see, tell me who your friends are, and I will tell you who you are, because we usually often we share the same characteristics with the closest friends. The idea of the KNN is the same. So when a new example arrives and we want to predict the class label for that new example, you can find who are its nearest neighbors or friends, and based on that you can find what was, for example, the class label value for those nearest neighbors, whether the majority, for example, if you have two classes, yes and no. If the majority were yes, then for the new example you can also predict yes. So this is the same. For example, in this picture, the new person seems more similar to this group or these neighbors, so belongs to this group of people. You see like group of people interested in food, interested in studying, interested in like shopping. So that's the same idea. So a new example is assigned to the most common class among the K examples that are most similar to it. So when a new example arrives, as I mentioned before, to determine which class label it belongs to. So for example, here, this guy this is the new example, and we want to see which class it belongs to. So we have to calculate the distance between this new example with all the examples that we have in the training set, and based on that, and based on the number of the K is hyperparameter. We later discuss how to find the proper K. But for now, let's say, for example, if K is 3, then we want to find the three nearest neighbors. So K defines the number of nearest neighbors that we want to find. And so you can, as I said, you find the distance to all the training examples. So those people are all in our training examples. And then you find the like for example 3 nearest neighbors. Now your training tuples are defined by set of attributes, right? So when I talk about like the k nearest neighbors in terms of the distance, which means how similar or dissimilar they are, you want to see how this new person, new customer, or new example in general is what is its distance to all of the other training examples. So our training examples are defined by, let's say, n features, right? So you have a table, you have like a few examples or tuples which are the rows of your table, and you have several features which are the columns of your table. The feature could be, for example, age, income, or any other feature. So based on like these similarities between features of your new example with features of the training tuple, you can find the distance. So there are several measures for calculating the distance. Like calculating distance is one, cosine similarity is the other one, Manhattan distance is the other one. So there are several distance measures. Euclidean distance is one of the most popular ones. So here, for example, the class label is the class label response is assigned to this new example. Why? Can you say why? So this is an example of, let's say, KNN when k is 3. We want to find 3 nearest neighbors to this guy in black and white. And so we found the 3 nearest neighbors. What are the class labels for these nearest neighbors? Yeah, response, response, no response. So we have 2 response, 1 no response. And we use a majority voting. We have 2 response, 1 no response. Therefore, we select the response as a class label, right? Do you have any question? So what if we have 2 response, 2 no response? So say we have like that. That's why most often like choosing an odd number for k would lead to like a tie, may lead to a tie in a voting, because for example, if k is defined as 4, you find 4 nearest neighbors. You may like face a case where 2 belong to, for example, yes, class yes, 2 belong to class no, or let's say k is 6. Then 3 may belong to class yes, 3 instances may belong to class no, and then there are different ways to like accommodate that, to address that. Like for example, it depends on the implementation, the specific implementation of the KNN that you use. So for example, if you're using the scikit-learn library to implement the KNN, how it handles might be different from like other implementations. So there are different ways, like they may randomly choose, they may use the first one, or they may, for example, assign a value to the class labels. For example, consider 1 for yes and 0 for no, and choose the one with greater numerical value. So for example, let's say we have 2 yes and we have 2 no, right? And then we don't know, these are our 4 nearest neighbors, right? And now we don't know what, for our new instance, should we assign yes or no, because we have like 2, 2. And in this case, as I mentioned, there are different ways to address that. One way is, for example, like randomly select 1, like either yes or no. One is assigning a numerical value to each of like these class labels, like for example, assign 1 to yes and assign 0 to no, and choose the one that has the higher value. In this case would be yes, right? Because 1 is assigned to yes. and many other different methods that I will explain if you have time today. So the k-nearest neighbor use instance-based learning, which means that we build no-mode model. Like KNN is not like most other classification models that you have like a training, like you build a training model. So you still have your training data, but you don't build any model based on that. And so it basically stores all the training examples, and you calculate the distance of like the features of your new instance with respect to the features of all the training examples. Now you can imagine if you have lots of, like if your training data is so huge, it could be computationally expensive. So this like KNN method may not be very efficient. It may work on like small data sets, but sometimes it also lacks efficiency because it should calculate the distance to all of like those training examples. So as I mentioned, each example is represented with a set of numerical attributes. We have seen like in the training examples that we had before the training data is often like represented in form of a table with rows and columns, right? Where the value of the columns are your attributes. For example, this could be age, income, and number of credit cards. And here are your tuples, right? For example, you have John, Rachel, and other instances. Now we have some values here. Now imagine there is a new instance arrives, like for example, Mona arrives here. And we have the value of age, we have the value of income and credit score. And for example, we want to predict the value here. So the way that it works is that it calculates the distance of like Mona with respect to all of these features compared like with respect to all the other instances, features of all the other instances, using one of the like the distance methods like the Euclidean distance to find which instances are closest. Like for example, if we are like defining k as 3 in KNN, we want to find 3 nearest neighbors, right? And then we have to calculate the distance with respect to each. So that, for example, distance of John to Mona, distance of Rachel to Mona until the end, right? And then we find the 3 based on the value that we found for the distances. We select the 3 most or the k most closest neighbors. And how did we? Just a quick question. Is someone coming? Oh, I forgot my question. Okay, so back to the example. So for example, we have John. We have several features for John. For example, age is 35, income is 95K, number of credit cards is 3. Rachel, again, we have the age, income, and number of credit cards. And when we talk about the closeness, it can be defined in terms of the Euclidean distance between 2 examples, not necessarily the Euclidean distance. It could be like, as I mentioned, it could be cosine similarity, it could be Manhattan distance, or other distance measures. So here is the formula for Euclidean distance. So for example, let's say you want to find the distance between x and y. So here, x is, for example, John, y is, for example, mono, right? How x and y are represented by set of features. So x is defined by a set of features, for example, from x1 to xn, because I is from 1 to n. And then we also have y, which is y1, y2 to yn, right? And then the distance of x and y are, wake up, y is 1 to n, xi minus yi 2, right? So this is the Euclidean distance. And so based on this formula, based on the formula of the Euclidean distance, now we want to have an example to go over an example together to find the distance of our new example for which we want to predict the class label with respect to all other instances in our training data. Okay, so for example, just to get you familiar with how everything works, based on this formula of Euclidean distance of John and Rachel is calculated as a square root of the distance between each feature. Like, for example, for the age, if you have, let's say, 35 here and 41 here, income you have 95K and 1215K, and number of credit cards 32. So how do we calculate the distance between John and Rachel? We say, okay, d of John and Rachel is equal to square root, right? The formula we are using the square root of the distance of all the mutual features. For example, distance between 35 and 41, root of 35, 41. And the reason we are using the square root is because we don't have to deal with the negative numbers here, right? Plus the next feature, 95 minus 2050 plus 3 minus 2, and then you calculate the distance based on this. And you have to do the same with all other, the training examples to be able to predict the class label. Now let's do an example together. Wake up. And so we want to find the 3 nearest neighbor in this example. We have age, income, number of credit cards, and response. In our training example, we have five instances, right? We have John, Rachel, Hannah, Tom, and Nellie, and 3 different features: age, income, and number of credit cards. Now, can someone explain how we can predict the class label response for David? Yep.
I guess we get the distance between each 2 pairs, like John and David, Rachel and David, and each of them, and then we compare the distance of each of them with David.
Exactly. So you can actually add another column. Let's say you have here the customer, age, income, number of cards, and response. So for we want to predict for this new instance. We have 35, 22, 9, 25 here. So it's a good idea to add another column here, right, to calculate the distance to David. So for example, the distance of John to David, distance of Rachel to David, and so on. Now, when we calculate the distance, we can use for example, the Euclidean distance, right? For example, based on the formula of the Euclidean distance, the distance between John and David is like the square root of 35 minus 37 plus 35 minus 50 plus 3 minus 2, and this equals to some number. And we continue the same procedure for like calculating the distance of each of like our training sets with respect to the instance that we want to predict the class label for. And let's say we calculate the distances here, and then we have some numbers. So for example, this is, let's go to see what were the numbers. So here you can see all the calculations. So we computed the distance of each of the customers with respect to David. And based on these numbers, which are 15.16, 152, 122, and 1572, which are the three nearest neighbors? Yep. So I marked them in bold, so you can see that they are the closest or the nearest neighbors. The reason is because they have the smallest distance with respect to David, right? So they are closest. And so now what we have to do is to check. So the value of the John, so the distance of the John and Rachel. And actually, I marked all of them in bold, sorry. But the closest neighbors are John. The three closest neighbors are John, Rachel, and Nelly. So here. So we have to check what are the class labels for these. For example, for John and David, the response was no. For Rachel and Dave, the response was yes. And for Nell and David, for Nell, the response was yes. Now we use the majority voting. We have one no, two yes. Therefore, we predict yes for David, because we had two yes versus one no. So here, the ones highlighted in purple, they are the nearest neighbors. Yes?
How far, do the numbers have to be for it to not count as nearest neighbor? Like, if there's another entry that was like 18 or like 20, would that still count as nearest neighbor?
It depends on the number of k. So it could be like, for example, let's say in this example, if we wanted to find the three nearest neighbors, and the value of the distances that we found were like this. say these numbers are like this. So 15.16, 15, 150, and nil and what was it? Yeah, nil distance was I want to find another number. So we have 122 here. Let's say this one is 80, as you said, right? We have 80 here. And we want to find the 3 nearest neighbors. So we have two 15.16 and 15, which are close. What is the next closest one? Between 150, 122, and 80. Yeah, 80. Even if it is like 121, it is still the closest. Because we want to find the 3 nearest neighbors. So you have to write all the distances. So distance 1, distance 2, distance n, and find the k distances that are less than the others. And so as I mentioned, we may face some situations when, for example, we have defined k as an odd number, like for example 4 nearest neighbors. Half of the neighbors belong to class yes, half of the neighbors belong to class no. As I mentioned, depending on the implementation of the KNN that you're using, there might be different strategies to address that. So for example, it could use random selection, it could use like weighted voting, or for example, assigning like numerical attributes to the classes, which I mentioned, for example, assigning 1 to yes, 0 to no, and then say, okay, because 1 is greater than 0, so yes has more value than no, and then you pick yes, for example. And you may also, like, if you see, not that even within the nearest neighbors, the distances are not the same. For example, if you use the weighted voting, there are like different, like based on the distances that each of like these customers have today with, they may have different influence. So the ones that are closest have more influence compared to the ones that are a bit far. So for example, if we're looking for 4 nearest neighbors, 2 yes, 2 no, and we want to see, or for example, we want to find 2 nearest neighbor, make it simpler. And 1 is belong to class yes, 1 belongs to class no. We find which distance is closer, right? That's weighted voting, and then choose the one with like more weight. So here the predicted response for David is yes, based on the voting. And by default, the KNN classifier use a simple majority voting mechanism. So for example, if we have 2 neighbors from class yes, 2 neighbors from class no, the class with the smallest label is choosing. So the one that I explained. If, for example, yes is 1 and this is no. So the one that is have the smallest numerical label. Oh, sorry. So I have to correct myself. So here you choose the one with a smaller number, because the numerical value that you assign to these labels is considered as the distance. So for example, in this case, 0 means smaller distance. So one of the problem with the KNN is what do you think could be the problem here? So in this example, I actually marked the problem in red. Yes.
One of the values is like going to affect distances like normal states, because the other numbers are like a smaller factor.
Yep. So the problem here is that different attributes have different scales. For example, here you can see that in that example, the incomes are in the scales of thousands. Like for example, we have $30,000, for example, as income. So these are in the scale of thousands. While, for example, the age or, for example, number of credit cards have like other scales. So the problem that it causes with the KNN is that it favors those attributes that have like highest range of scales. And in this case, for example, it favors income and it considers it as like having more weight. And so that is one issue. How can we resolve this? How can we address this? This could be very easy. Yeah, with normalization. So we have to always normalize the values so that it doesn't, so that your distance will not be dominated by the attributes that have large numbers. For example, in this case, the income. So we don't want our distance. So you see, like in the distance that I calculated there, square root of 35 minus 45, and then 95,000 with like 200,000. That attribute is affecting the distance very much, right? Because it adds like a value like in thousands to the distance, and it negatively affect the distance calculations. So we have to normalize that to, like, for example, fit it into a range of, let's say, 0 to 1, for example. You can use min-max normalization as we've learned before, or like max normalization. There are different methods for normalization. And so here's an example. The income in this table, if, for example, the highest income, let's imagine the highest income was 200K and the lowest income was 0, and now we want to normalize the value of income. For example, if John income is 35,000 and you want to normalize it, is 35,000 minus the minimum, which is 0, divided by max minus mean, right? So you always divided that value minus mean divided by max minus mean. So because mean is 0, you have like 35K divided by 200K when you are normalizing it. And another method to normalize, which is used in these slides, is max normalization. You just simply divide all the values by the maximum value. For example, let's say, what is the maximum age here? 63, right? So you divide all the age values by 63. This is called max normalization. So you just divide it by the maximum numbers. So what would be the normalization impact on the distance? So we said that what was the issue with the KNN when we didn't normalize values?
Some features with larger values make the result like unequally larger.
Yeah. So the normalization can address this by making sure that all the features are contributing equally to the distance measurements, right? And without normalization, attributes with larger ranges can dominate the distance attributes, as your friend mentioned, leading to misleading results. And again, as I mentioned, normalization ensures that all the features contribute equally to the distance metric by, for example, fitting them into a range of, let's say, 0 to 1. And here's another example. Now, this time we want to calculate with normalization of distances with normalization of variables. So we want to find the response, the class label. We want to predict the class label for David using the KNN algorithm. So how things work, first of all, we have to normalize all the values, right? We are using the max normalization here. So in case you're wondering why we didn't, for example, do 55 minus minimum, what is the minimum age? 22, divided by maximum age is 63. So this is minimum age. the normalized value of 55, as we learned in like previous lectures, is the value minus mean divided by max minus mean. This is not what is calculated in this table, right? So we simply divided each value by the max. So we use the max normalization instead of mean max normalization. So after we normalize all the values in the table, we find the distance using the Euclidean distance formula, which is the square root of the distance between like each like mutual features between the like your new instance with respect to all the training examples. So for example, based on this calculation, let's say we already find the distances of, for example, John to David, distance of Rachel to David, distance of Hannah to David, and so on. And we after we find all the distances, because we want to find, let's say, 3 nearest neighbors, in case 3, we have to see what are the votings. And because we had 2 yes, 1 no, we selected yes here. And here are like the detailed calculations in case you want. So I just put the detailed calculation in the first row just to save a space. You can use the same formula for Rachel, Hannah, Tom, and Nellie. And the reason that we chose yes is because the 3 nearest neighbors here are John, Rachel, and still Nellie. Even after normalization, we still have the same neighbors. Yes, and so the predicted class label for David is yes, because we have 2 yes and 1 no. So we have another problem with KNN. So one problem is that if we don't normalize the values, some instances, some features may contribute unequally to the distance measurements. But we have also another problem. What is that? So the problem is, what if we have an attribute with the nominal values? So we have, for example, married column here. The married column could be yes or no. So we don't have any continuous value here, right? We don't have any real value like the age, the income. So we have yes or no. What do you suggest for this? How can we address this? So when we want to calculate the distance of David with respect to all of these customers, how can we calculate? Because what we have to do based on the Euclidean distance is to just find the square root of xi minus yi. And let's say xi minus yi for x1 minus y1 here would be yes minus yes, right? Or yes minus no. Yeah, that is one way. Exactly. So because it is not possible to do subtraction on nominal attributes. You cannot subtract yes from no, right? You can assign numerical values, for example, assigning 1 to yes, 0 to no, and then do the calculations based on that. So here, converting the method 1 is converting the nominal attributes to numerical attributes. So for example, assigning 0 to no, 1 to yes, or if we have more than 2 different feature values, if we have, for example, color column with the values of yellow, red, and different colors, we assign different numbers. What do you think is the problem with this one? Imagine you want to calculate the distance of David to, for example, all these customers, and you have a column with a feature that contains nominal attributes of, let's say, color ranging from blue, red, white, and all the other colors.
So the result will be biased.
Yeah, why?
Because you're simply assigning random values to the nominal attributes. So like you have assigned 1 to blue, but you would have assigned 3 as well. So if you perform different calculations, then the values will be different.
Yeah. So because let's say in this table you have you're assigning, let's say you have a color here, so you have a column color here, and for the colors you have red, blue, yellow, and let's say black. And we assign like numbers like 0, 1, 2, 3. Now when we are calculating the distance, what happens is it's like when you calculate the distance, when you stop track these numbers, let's say for example here for the new instance we have like blue, which is 1. This distance, like 0 minus 1, 1 minus 1, 2 minus 1, or 3 minus 1, which will give you different numbers. For example, it may give you more numbers for the color black because we assigned a higher value to black. But it doesn't mean that, like, it doesn't mean any real value. We just assigned random values, but it doesn't mean that black, for example, should have a higher distance, right? So it caused bias in our data. So that was one issue. What could be the other method to address this problem with the nominal features? What else do you think?
So we can try to binarize the nominal values. Like we can try to binarize the nominal values, for example. Binarize it, like try to binarize the value.
Like 0 to 1, 0, 1.
Like we first choose a scale for the nominal values. We discretize those values, and from there we can binarize to have a more accurate result. Like that's like it's just a thought.
Okay, so the other method is, for example, you say if xi and yi have the same like value, like for example, if both are, for example, yes, or if both are, for example, red, then the distance is 0. If they are different, the distance is 1. So this is for nominal attributes. So whenever they are, so for example, here for David, if the color was, let's say, the color was red, the distance of David to, for example, John, which is red, the distance is 0 because they are the same. But the distance with all the other ones are 1. So this way, we don't differentiate blue, yellow, black, right? We don't put different weights to different colors. And so this is the case with the nominal features. And if the feature was not nominal, if it was continuous, then we can use the norm of like the absolute value of, or the distance of the normalized values between xi and yi. So I hope you understand what was the problem here and why we did this. So because like the values that we assigned to nominal attributes were not the real values, right? We just had like random values, and it doesn't have to interpret it. The problem was that it could be interpreted as like a real value for a distance, which was not the case. What about the missing values? So what if we have a missing value? Yep. Yeah, but in general, like when you have a missing value, because sometimes you, like it happens in data mining that sometimes you want to keep the missing values and you don't fill them. Like in that case, if you have a missing value, you just consider the maximum possible distance, which is, for example, 1 here. And So here's another example. And I want you to think about how to find the response for David in this case. We have one nominal feature here, which is the married. We have yes and no, income, number of cars, and response. So I give you like a few, like a 1 minute to think about it. You also have an example. So you basically have to find the distance of David to all the customers. So I already showed you how to calculate the distance of David with respect to John. You have to do the same for other features. So the distance of David to John would be yes minus yes, right? Which is 0. We said whenever we have nominal features, if the values are the same, which is the case here between John and David, both are yes, then we say that the distance is 0, right? Because both of them are yes. Is it clear? Is the 0 clear here? Okay, distance of David and John is 0 plus something plus something. The first 0 is because yes minus yes, we said whenever we have nominal features, which is in the case of the first features, which is married here, because both are yes, the distance is 0. For example, Rachel, the distance for the married feature would be 1, because David is yes, Rachel is no. So the distance would be 1. So whenever both are yes is 0, whenever one is yes, one is no, the distance is 1. And then you have to find the sum of all these like absolute numbers of distances. And you also don't have to forget to normalize the values to avoid the like affecting like those features with like higher ranges of values affecting your distance values. That's why we normalize all the values in the table. So here I calculated the distances for you. Yes?
How come we aren't getting like the square root and the squares?
Sorry?
Like, how come we aren't doing the square root and the squares of the distance? Like, we're not like 0.25 and then like, isn't it supposed to be squared?
Yep, when we had, like that was for finding the Euclidean distance, when we had all the attributes were continuous. And then we said, okay, what if we have also nominal features? And then we introduce here method 2. And if you see method 2, we don't do the like the Euclidean distance here anymore, right? So we are using this formula here to find the distance. And so here are the values for the distance. Now let's say we want to find the 3 nearest neighbors. Yeah.
But isn't taking the absolute value the same thing as doing the square root of the square? It would give you the same result. Because when
You can actually find you can use like any distance measures, like even not only like the Euclidean distance. So there are like different ways to calculate the distance, and you are using the same distance method for all the features, so that would be the same. Yeah, I just meant that because your friend asked why we are not using that, so I mentioned you're just following this method. So we say, for example, 0. The first one is 0 because we have like 2 yes, and then we follow the same procedure. So here are the calculations, and we have like the 3 nearest neighbors, which are John, Rachel, and Tom here. And now we have to check what are the class labels for these 3 nearest neighbors. We like for John and Tom, we have yes, so we have 2 yes. And for Rachel, we have no, so we have 1 no. Therefore, the majority voting gives us yes for David's response. So here I put some notes for you about KNN. So before I go to Kahoot, I want you to, we already explained some of this, but I wanted to also make a note about the setting the K. First of all, K is a hyperparameter. So like it's not like I tell you always fix k to 5 or 3 and that works. But like there is a rule of thumb which I wrote here, but you have to remember if you set the value of k too high or too low, it may become too overfitting or underfitting. Here in this specific case of KNN, underfitting is like the same as oversmoothing. Like oversmoothing is a subset of underfitting. And so if you set a value of high, value of k very high, let's say for example you say k is 20, what happens? Why is it caused to oversmoothing? Because you're like expanding your search to include like 20 neighbors, and let's say these like 20 neighbors we may include also the ones that are not really close to your example, like include like more, like your model become too generalized, right? Because you are like considering more instances into your model. So the model become too generalized, which caused the oversmoothing. And on the other hand, if you set the value of k very small, let's say if you say just one nearest neighbor, this is exactly what happened in decision trees with overfitting, right? Because your model is not too sensitive to noises, because you are selecting just one neighbor, and it like learn all the like nuances in the data, and it becomes overfit. So that's also the problem with setting the k too low. So it's a trade-off to like find the k, and there are different ways to choose the proper k. You can use, for example, cross-validation and find the value of k with that, or you can use, for example, like the errors, choosing different cause, find which one lead to like lower error value and choose that k. And a common rule of thumb is to set the k to the square root of the number of data points. So if you have, for example, 100 data points, you find the square root, and your k would be the square root of that data points. And as I mentioned at the beginning of the class, there are some strengths and weaknesses for the KNN. First of all, it's simple to implement and use. It's easy to explain the prediction, and it can learn complex target functions, and it can be used to like in regression. Why? How can we use KNN for regression? So in like regression, we were predicting the value of the target variable, right? So how KNN can do that? Yeah, like in terms of like the calculation.
Predict the final number on the line. Like there are many points on the line, each of them has a number. The point around it gonna get like assigned to one of the points.
Yeah, it gets the average, or like let's say the weighted average of the target variables. Let's say if you have like k nearest neighbors in your feature space, and then it can predict the value of the target variable based on the average of those k, the value that it has for those k neighbors. And they can also be used for numeric prediction, and in this case, a classifier returns the average value of the real valued labels. So instead of like predicting yes or no, it returns the real value. And in terms of the weaknesses of KNN, as I mentioned, because in KNN you have to, it basically is, it's calculating the distance with respect to all the training examples, right? And let's say if you have a large data set with like a lot of instances and a lot of like different features, it's computationally expensive, so it's not very efficient. It needs a lot of memory space to run compared to, for example, decision trees. And it takes more time to classify a new example. And also, but the advantage was that it doesn't need a training set, right? Because we don't, it doesn't need a training model, because it doesn't build the model like most classifiers. It just basically store all the training sets and then calculate the distance with respect to each instance. So here is just a comparison between decision tree and KNN. And basically, decision tree provide a very clear structure. You can see the path, the decision path within the trees, and KNN could be good in scenarios when our structure is not well defined. Most use cases for KNN, like some of the common use cases for KNN is, for example, in recommender systems, when you find, for example, similar neighbors, like, for example, similar customers to you, or similar, for example, products. And what else? Yeah, in image recognition, for example. In terms of interpretability, decision tree is more interpretable, as I mentioned, because you have like a clear structure. You can see the decision path, while in KNN, KNN relies on proximity, right? And so it is less interpretable. And in terms of efficiency, again, I explained, because it stores all the training data, it doesn't have any model, and it calculates the distance with respect to all the features in the instances, the training instances. It takes a lot of space in the memory. Okay, let's go to Kahoot.
Your attention, please.
Three people are missing. Who was not able to join? Okay. Yeah, but I don't know who is over here.
I mean, does the name matter? Should I change it?
Oh, no, it's fine. Okay, sounds good. We can start. So I'm going to use like these as your participation marks. Try to be as active as possible.
How do you even link it to eClass?
I'm sorry, because it has timing answer, and I will answer your question later. So
Well, I mean, how are we going to link like the Kahoot to eClass? You said this is a participation.
I sent the links. Okay, so the question was, what is the primary method used by KNN to determine the class of a new example? So 8 people answered blue. What? Average of all training examples, most common class among the nearest neighbors. So the, the correct answer is the most common class among the nearest neighbors. So the 8 people that answered blue is the correct answer. So the most common class among the nearest neighbors. I apologize. So who was? How can I read this? Ursan. Okay, you were really lucky. Okay, next question. I hope I didn't do the same mistake here. In KNN, how does normalization of attributes affect the distance calculations? Nice. So it ensures all attributes contribute equally to the distance. And so 2 people said it allows attributes with larger ranges to dominate the distance. So that was actually the red one. The red option was the problem with the KNN, and the normalization was to address this problem. Good, Ryan. Who is Ryan? You? Nice. Okay, so true or false? KNN requires a training phase when a model is built before classification. Basically, it asks whether it needs to build a training model. No, it doesn't. You have a training set, you have a training data, but you basically don't build any. As I mentioned for KNN, what is the advantages of one of the advantages of KNN is that it doesn't need to build any model. Okay. KNN can only be used for classification tasks and not for regression tasks. We already addressed this. So I was really wondering who said true. We explained how we can use KNN for prediction in regression. Yeah. So we can use KNN for both classification and regression. The same applies to decision trees. You can use decision trees for classification, which we learned in this class, but you can also use decision trees for regression, which we didn't include in this class. King. Okay, next. Which formula is used to calculate the Euclidean distance between 2 points in KNN? This should be easy. So the green option, this is the square root. That was the closest thing I could find. Okay. I'm curious to see who was the one person selected blue. Okay. It was a system error. But that's not Euclidean distance. Okay, so next one. What is the role of the parameter k in the KNN algorithm? Right, it specifies how many nearest neighbors to examine for classification. For example, if k is 3, means we have to find the 3 nearest neighbors. Okay. The k nearest neighbors algorithm doesn't require training phase. We already had this, so this question is repeated. Anyone who answered this wrong get a negative number, get negative point here. Okay. Oh, one person. Who was it? Okay, Ryan, you're... Yeah, sounds good. Increasing the value of k always improve the accuracy of KNN. As a hint, I mentioned what would happen if you increase the value of k, right? So we said if you set k too high or too low, may lead to either over smoothing if you set it too high, or if you set it too low, it becomes too sensitive to the noise and it like becomes overfit. So when it causes overfitting, over smoothing or underfitting by setting the k too high, it means that it doesn't help the accuracy, right? So which statement best describes the role of distance metrics in KNN? So I want to see what does it, how we can interpret like those distance measures. What do they calculate? Right, so they determine the similarity between data points. So because we said we want to find the k nearest neighbors or the ones that are closest, we said that the closeness can be defined in terms of different distance measures, like for example, Euclidean distance, Manhattan distance, or other measures. And so it defines how similar or how dissimilar like 2 points are. So the last question. What happens if the number of neighbors k is even? Like the example I mentioned, if you define k as 4 and then you have 2 yes, 2 no, how to decide what class label. Yes, it can create ties in class voting because it can say like we can have equal number of classes, instances belonging to one class and the other half belonging to the other class. Okay, so let's see who are on the podium. So could I ask who are King and Chawan? Is number 1. Ryan, nice. Okay, good. Who are number 2 and 3? Number 2 and 3, nice. Okay. Okay, thank you everyone. Thanks. Next session, I think I will move forward with the decision rules. We'll spend at least one session on decision rules, and next week we'll start association rules.